Mr. McBride. This is TEJ20, Circuits, Parallel and Series. Ontario would like for students to safely construct and test electronic circuits. We're going to learn how to effectively construct parallel and series circuits today. Yesterday we talked about multimeters. Today we're going to review resistors in series and parallel from your grade 9 science class. Talk about how electrons are lazy. And we're going to cover converting units, something very important in computer engineering. So, resistors in series. I'd invite you to, before we begin, think about what a resistor does in a circuit. There are two very good answers to this question, and one of them is going to be particularly useful today. So think about this. What's the answer to what a resistor does in a circuit? Hopefully, you answered a resistor either removes energy from an electron, which is true, or you said, and maybe more likely, a resistor slows down the current in a circuit. And it's that second piece of information we're going to use a lot today. So a resistor slows down the current in a circuit. Now, my next question for you then is what happens if you add a resistor to an existing circuit? So what happens if we take the resistor here and put a second one after it? And hopefully your answer was it'll slow down the current even more. And that is basically true. Now, as far as the math goes, we can be more specific than to say it slows down the current. When we add resistors one after another, resistors in series, the resistances add up. Very straightforward. So if we take this case with 3 resistors, R1 being 3 kiloohms, R2 10 kiloohms, and R3 being 5 kiloohms, we can calculate the total resistance of the circuit by simply adding them up. So our givens are the 3 different resistances. Our unknown is the overall or total resistance. We add them up and we get 18 kiloohms. Notice that the resistance has gone up. Now, what would happen if we add too many devices then to the same circuit based on what we've just seen? What do you think happens? If we just keep adding one device after another in series to a circuit, what happens? Well, eventually the current gets so low that no device will run, not even an LED. So if we keep adding devices to a series circuit, the overall resistance gets so high the current becomes too low to run any given device. And this is where we start to talk about a different approach to designing circuits. So far, we've focused on these simple series circuits that have only one path for electrons. And the current is the same through every point in the circuit. We call this the Congo line principle. So if we choose to measure the current at any, we call them nodes, at any node in our circuit, the current will be exactly the same. There's another option. So before we talk about that option, let's talk about one more problem with series circuits. Imagine your house were wired like this series circuit. Imagine each light were wired in series. Can you see the difficulty with this approach? Again, I invite you to, if you haven't figured it out yet, pause the movie and think about it for a second. The problem with this design is that every light in the house would be on or every light in the house would be off. Remember that the current is the same through any point in that circuit. So in cases where we need to have a single power source, like the main power that comes into your house, but we need to have different currents. We need a different design. And this is where parallel circuits come in. Parallel circuits are circuits where we have more than one path for electrons. If we look at this circuit here, we have the path through resistor 1, the path through resistor 2, and the path through resistor 3. Each one is independent to the others. And current will flow through each path. But how much through each path? Well, in fact, we can figure that out. Let's talk in general terms first. So, if we look at a given circuit, we can say that the electrons want to get from the negative pole of the battery to the positive pole of the battery. But electrons don't want to do more work than they have to. And so if there's more than one path to the positive pole, the electrons will prefer the easier path. In fact, it's a little more mathematical than that. But we can take this as our first pass on looking at our circuit. The current flows through the 1.5 ohm resistor. Well, there's more current through it than through the 3 ohm resistor. Can we quantify this? Absolutely. And the answer comes with the fact that parallel circuits are independent circuits, individual circuits, even though they're connected to the same power supply. Ohm's law applies to both resistors. Just because we wired them up to each other doesn't mean Ohm's law doesn't apply. So, Ohm's law can give us then the current in this circuit. The current through R1, well, Ohm's law, I equals V over R. The current's equal to 2 volts over 3 ohms, or 0.667 amps. Now, the current through resistor 2, Ohm's law again applies. I equals V over R equals 2 volts over 1.5 ohms equals 1.33 amps. So not just that it's more current, we know exactly how much. Now there's a special parallel circuit that we should discuss briefly because students sometimes make the mistake of creating this parallel circuit in the lab and bad things occur. So have a look at this circuit. This is a very special parallel circuit. What is the current through the 1.5 ohm resistor? We just calculated it. It's 1.33 amps. But the current through the other path, you might be tempted to say, oh, there's no resistor, the current will be 0. In fact, the opposite is the case. If we forget the resistor in the parallel path, we get extremely high current, almost infinite current through that short circuit. So even though there's a resistor in the circuit, because there's a second path that has no resistor, we have a short circuit. So please be careful to make sure every possible path for electrons has something to reduce the current. Now you might ask yourself, wait, can we get the overall resistance of a circuit that has parallel resistors? And I'd invite you to think about that for a second. What's the answer to that question? Well, you might have answered, sure, we can get the overall resistance. We can add up the currents for each one of the resistors, and then based on the total current, back calculate the effective resistance. But there's an easier way. So with regards to resistors in parallel, we know that the current distributes between them. We know the overall resistance goes down because the current obviously goes up with each resistor we add. Well, in fact, the mathematical expression for this is 1 over the overall resistance is equal to 1 over R1 plus 1 over R2 plus 1 over R3, etc., etc. So for this circuit then, we can calculate the overall resistance. So let's have a look at one. We can ask ourselves, what's the overall resistance of this circuit here? Givens, R1, 10 kilo ohms, R2, 2 kilo ohms, R3, 1 kilo ohm. Our unknown is the total or overall resistance, and our equation is 1 over RT equals 1 over R1 plus 1 over R2 plus 1 over R3. When we substitute in, we get this, and hopefully when you walk the algebra through, you get the overall resistance equals 0.625 kilo ohms, or 625 ohms. Notice that the resistance of the overall circuit is less than the resistance of any of the resistors that make it up, and this is typical of resistors in parallel. Okay, a quick hint for you with regards to solving resistor and parallel problems. There's a lot of fractions involved, and some of you will be less comfortable with fractions than others. The key is, if you're not good with fractions, simply get out your calculator and do the calculations carefully. Don't attempt to simplify the fractions if that isn't your skill set. Okay, you should be able to discuss the advantages of parallel circuits by now, but let's sum them up quickly. When we have devices wired in parallel, we can power many of them with one potential source without the resistance becoming too high. In fact, the overall resistance goes down. We can have independent control of multiple devices, so we can have switches for each individual device. And something that was implied but we haven't described in detail yet, we can have devices on a single circuit that require different levels of current. For example, we can have a motor and an LED on the same circuit, even though a motor requires very high current and an LED requires very low current. Okay, you may have noticed that I did a trick there with my resistors in parallel. I converted kilo ohms to ohms very quickly, and we didn't discuss that. Well, it's probably time now for us to discuss the idea of converting units. Before we do this, I'd invite you to once again think about a couple of questions. So if you're in the school right now, how far is it to the office? Whether you're in the school or not, how far is it to Los Angeles? Now, you will have naturally made a conversion in your head. You will have probably estimated in meters with the distance from the classroom to the office versus kilometers from where you are to Los Angeles. Why'd you do that? Why did you use meters for one and kilometers for the other? Well, the answer to this is what we want to talk about today. In electronics, like in distances, we use a wide range of values. A power supply for a laptop will give us about 1 amp. An LED can only handle about 0.040 amps before it burns out. Some of the circuits we need in computer engineering need about 5 millionths of an amp. Some of the circuits we design need 1 million ohms. We have a wide range of values in computer engineering. And when we do this, we can be tempted to simply start adding the zeros. But if you notice, when you were looking at those numbers, you probably started counting zeros to try to figure out what those numbers were. In fact, we can make easy mistakes. We can easily make mistakes when we count those zeros. Humans work well with numbers that range from about 1 to about 1,000. That's the way our brains work. And so we tend to want to keep the numbers we work with in that range. And we do this by introducing prefixes. And you naturally did this with that distance to Los Angeles, adding the prefix kilo or 1,000 to keep the numbers less crazy. You didn't want to report that it was 3.5 million meters. You instead said something like 3,500 kilometers. Now we'll use a bunch of different prefixes in computer engineering. Here's a few of them here to get us started. I'll give you a more comprehensive list afterwards. So mega means million. Kilo means 1,000, as I mentioned. Milli means thousandth. So we will tend to use these things. By the way, isn't it interesting that you probably did not say 3.5 megameters? We don't tend to use that prefix when we talk about distances in our lives. So, let's do a few examples. Let's try these out. 400 ohm resistors in series. What's the overall resistance? You might remember that resistance overall in series is additive. So 400 plus 400 plus 400 ohms equals 1,200 ohms. We could leave it like this, but we tend to want to keep our numbers between 1 and 1,000. So what do? We can convert to kiloohms. Now, I like to call the approach to unit conversion multiplying by 1. You can take any approach you want. You need to realize that there are 1,000 ohms in 1 kiloohm. And so you can divide by 1,000 to get 1.2 kiloohms. Or you can multiply by 1. Multiply 1,200 ohms times 1 kiloohm divided by 1,000 ohms. Since they're equal, that is the same thing as multiplying by 1. And as we all know, if you multiply something by 1, you get the same value. So 1,200 ohms equals 1.2 kiloohms. Let's try a current example. The recommended current for a given LED is about 0.02 amps. What's that in milliamps? Well, there are 1,000 milliamps in 1 amp. So again, we can use our multiply by 1 trick. Multiply 0.20 amps times 1,000 milliamps per amp. 1,000 milliamps divided by amps. And if you're the type who likes unit cancellation, we can cancel the amps and the only units remaining are milliamps. So 0.202 amps is 20 milliamps. Three 1.0 mega ohm resistors in series. What's the resistance of the circuit in ohms? Usually we don't want to do this conversion to avoid getting very large numbers, but for some reason we want this in ohms today, so we will do that. First off, we use the resistors in total equation to get 3.00 mega ohms. And then we need to realize that there are 1 million ohms in every mega ohm. Multiply by 1, so multiply by 1 million ohms per mega ohm. We can see that the mega ohms cancel, and we get 3 million ohms. So here are the prefixes that we'll be responsible for in computer engineering. Some of the larger ones we tend to use in the computer world, tera and giga. Some of the smaller ones we use primarily when we're talking capacitance, which we'll talk about in a few days. You should be able to do any of these conversions. So, to make sure that you've got series and parallel down, you should go ahead and complete the series and parallel activity, observing these circuits in action. Let's sum up. When we place resistors in series, the current drops. Resistances add together. There's lots of useful circuits that have more than one possible path for electrons. We call them parallel circuits, and the overall resistance will drop. This is because the currents add together. Ohm's law applies to all paths in a circuit, even a parallel circuit. But we don't have to use Ohm's law all the time. We have two new equations for calculating the overall resistance of the circuit, both in series and parallel. We just have to make sure we use the right equation for the right time. For your homework, please complete the worksheets and the activity. Thanks very much. Have a great night.